Our second speaker in this session is Yushan Liu from Princeton University. She's a third-year graduate student.
Okay. Good afternoon, everyone. I'm Yushan Liu from Princeton University. Today, I'd like to present SmartWalk, a social network security enhancing system that incorporates adaptive random walks. This is joint work with Sholing Ji from Georgia Tech and my advisor, Pratik Mittal from Princeton University. First, here is the outline of my talk today. First, we will begin with a background of how random walks are applied in security applications, followed by an introduction of the classical paradigm. Next, I will introduce a new concept that measures the required random walk length. After that, I will give a system overview of the SmartWalk system and also present experimental results for evaluations in security applications. Finally, I will conclude my work. Nowadays, online social networks such as Facebook or Twitter are driving new forms of social interactions. Users of social media, they friend each other, they follow others' tweets, they leave a comment, they post updates. And in this way, social trust relationships are established. This kind of trust relationships can be represented by social graphs and has been widely leveraged by a range of security applications, such as recommendation systems, reputation systems, and also civil defense mechanisms. Among the design of these applications, a very important approach used is to perform random walks on social graphs. What is a random walk? Here we give an illustration. This is a social graph with the starting node marked particularly in red. A random walk initiated from this starting node will randomly pick one of its links and to jump to the next node at each step. Here is the example of random walks of length 3. You can see that given a starting node, random walk of length t enables us to visit t-hop neighbors and also help us get an understanding of the structural properties within t-hop neighborhood around this starting node. Since random walks can help us gather the structural information of k-hop neighborhood, and also it's a decentralized and very simple to implement, it has gained popularity in recent years and formed a critical foundation for many social network-based security systems and applications. Next, I will describe the classic paradigm of random walks and also its drawbacks. For random walks, a very significant and interesting parameter is its walk length, t. You can see that for t equal to 1, as we started, it will just limit it to a very close neighborhood. If we increase the random walk length, the neighborhood we can arrive at gets gradually larger and larger. For random walk starting from a certain node, if we keep increasing the random walk length, that is, for longer random walks, it benefits us by making it possible to visit and explore more edges and nodes, and thus can provide us with more mixed and balanced information from a wider neighborhood. However, in the meanwhile, the downside of longer walks is that the terminal nodes are more distant from the starting node, and thus they are less trusted by us. All these pros and cons of long walks has induced a poor trade-off. Has induced a poor trade-off between security and other desirable properties for random walk-based security applications. For example, in civil defenses, for longer walks, we can reduce the number of misclassified honest users, the false positives. However, it also gives the adversaries more power to corrupt the honest region, that is, put security at risk. And for link privacy preserving systems, longer walk can enhance the provided privacy at the cost of degraded utility. This kind of dilemma has made us think, how can we figure out a way to improve this trade-off between security and performance? Before we address this problem, we will first take more insights into the classic paradigm of random walks. We know that proof of work adopts fixed-length random walks in security mechanisms. That is, the random walk length for every starting node is identical. However, our observation is that actually different starting nodes may have different requirements for the random walk length. Here is an illustration of two different starting nodes. You can see that from the starting node in the left figure, with the same random walk length, t equal to 3, it has already reached a large portion of the network. However, for the starting node in the right figure, the area it can reach is very limited to a small corner of the network. To achieve the almost same impact size of the impacted area, the starting node in the right has to take random walk about up to 6 hops. If a classic fixed-length random walk scheme is adopted, then we will choose the worst case among all nodes. In this previous example, we will choose the random walk to be 6 to satisfy the maximum needs of these two nodes. We would like to propose adaptive random walks that takes a more flexible strategy. We will only feed the nodes with the minimum requirement. And in this way, we can gain more fine-grained control and thus improve the security and performance trade-off. In the following, we will examine these questions. First, how can we define the desirable walk length? To what extent longer walk become unnecessary? And second, how can we find a way to effectively predict the random walk length required for different starting nodes and also apply them? And finally, we want to look into the impacts on security and privacy systems. We will first answer the first question by introducing a new concept, local mixing time. Before we move on, let's see what will happen if we continue to increase the walk length t in the previous social graph. Recall that we start from t equal to 3, and now we increase it by 1, and it gets larger, and finally at t equal to 7, all nodes in the network can be reached, and the longer walk will not bring us more accessible nodes. And actually, if we continue to increase the random walk length t, and finally we arrive at a point t equal to n, where longer walk will no longer help us gather more structural information of the social graph. And in this point, we have arrived at a steady state. More formally, we put it in this way, the probability distribution of the terminal node has converged to a stationary distribution. Based on this tendency of convergence, we give the definition of local mixing time. That is, we measure the minimum random walk length for a certain starting node to be close enough to the stationary distribution, and this distance to stationarity can be captured by the parameter epsilon here. Note that epsilon can be tuned to satisfy different application needs. It can be strong convergence or a weak one. Next, we are interested to see how local mixing time are distributed in social graphs. Here, we plot the cumulative distribution function of local mixing time in 10 different data sets. If we look at the YouTube data set, that is the yellow curve, you can see that most nodes, a majority of nodes actually just require a very short random walk length, around 50. And however, the rest node, a small portion, around 5% of nodes, they will ask for a much longer random walk length. It can be up to 200. The similar observation have also been found for other 9 data sets. And we call this a heterogeneous and a long tail property of the local mixing distribution in social graphs. This is actually the reason why the classical fixed length worst case random walk length selection method is very inefficient, because a majority of nodes, they do not require that long random walks to approach stationary distribution. To propose adaptive random walks, the ideal approach is, of course, to compute the local mix time for each given node using brute force, and then set it to be the random walk length. However, the challenge here is that to compute local mixing time actually requires the global information of the entire social graph, and it can be very computationally expensive and time-consuming, especially for large-scale social networks. That is why we propose the smart walk system. Here is the system overview. The smart walk system will read a social graph and produces adaptive random walks upon request from security applications. It contains two components. The first component, the local mix time prediction algorithm, takes in a starting node index and returns with a predicted random walk length to the second component, random walk usage model. First, I will explain the intuition behind our prediction algorithms. Here is a community structure of a social network, and the colors differentiate different communities, and the size of the node is proportional to the local mixing time value. We observe that the local mixing time for nodes residing in the same community doesn't vary greatly, and the transitional changes. Sorry. Excuse me, I cannot get to the next slide. It's good. Yeah. And the transitional change of local mixing time actually often occurs at the margin nodes that connect various communities. This motivates us to employ supervised machine learning techniques to predict the local mixing time. Since that nodes residing in the same community, they share similar local structural characteristics. This can be used as features for us to map nodes to their communities. And also, due to a limited number of communities in social graphs, a small subset of nodes will be sufficient to sample the entire social graph. More formally, we use the probability distribution of terminal nodes in a k-hop random walk as features. Note that k here is relatively small to the maximum local mixing time. And a small subset of nodes, M nodes, are selected randomly as the training set. M here is also small. Next, we use these features and the training samples to fit a random forest regression model. To evaluate the fitness of our regression model, we employ two metrics: the root mean squared error, RMSE in short, and also the coefficient of determination, R squared. These two measure the difference and the correlation between the predicted value and the original values. You can, of course, the higher R squared, the lower RMSE, the better prediction we get. We compare the prediction results with varying parameters. First, we find that for a larger K, a wider neighborhood can actually provide a more accurate mapping between nodes and the communities, and thus produces better prediction results. And if we increase the training size M, it can help us fully sample the entire social network, and thus the prediction results are also improved. However, also note that when N exceeds 500, the improvement in performance become less obvious. Now that we have tools to predict the local mixing time for different starting nodes, how can we design the usage model to apply them? A fairly straightforward method would be simply set the length to be the predicted local mixing time of the starting node. As the work progresses, we simply decrease the remaining random walk length by 1, and finally we stop when the length diminishes to 0. You can see that in this node adaptive random walk scheme, the random walks become adaptive to the starting node. However, we also know that in this model, the random walk lengths are independent of the intermediate nodes, no matter those intermediate nodes are in a very high density area or in a very sparse area. This observation actually gives us an idea of another usage model, post-adaptive random walk model. In this case, every time we reach the next hop, we compare the remaining length of the starting node and also the local mixing time of the current node, and we choose the minimum between these two as the remaining length, so that when we reach a well-connected node, we do not need to bring unnecessary hops. In this example, you can see that the random walk length is reduced from 5 to 4, and we make the random walk length adaptive both across nodes and to the parts it has already covered. Finally, I will test the applicability of our adaptive random walk models in a variety of security applications. First, we consider civil defenses. Classic